Imagine a spacecraft, gliding silently through the dark void of intergalactic space. It has left the influence of our sun, drifting into the unknown, where gravity should be nothing more than a distant whisper. Every movement is predicted with stunning precision, its trajectory mapped by equations that have guided humanity's journey through the cosmos for over a century. But then, something impossible happens. A subtle, almost imperceptible force begins to tug at the spacecraft, pulling it ever so slightly off course. At first, mission scientists dismiss the anomaly, perhaps a software glitch, an unnoticed micro-thrust from its engines, or even the faint pressure of solar radiation. But the calculations don't lie. The force is real. And what's more, this isn't the first time something like this has happened. When they dig deeper, they realize this strange, unexplained drift has been observed before, in multiple deep space missions. The Pioneer anomaly, the flyby anomaly, the unexplained accelerations detected in the Voyager probes as they crossed into interstellar space. For years, these deviations were brushed aside as errors, minor inconsistencies that would eventually be explained. But now, as new telescopes peer deeper into the universe and space agencies push further beyond our solar system, scientists are starting to wonder, what if these anomalies aren't just mistakes? What if they're clues? Clues that something is fundamentally wrong with our understanding of gravity itself. For over 100 years, Einstein's general relativity has been our guiding light. His revolutionary insight that space and time are not fixed but bend and stretch in response to mass completely redefined physics. According to his equations, gravity isn't really a force in the traditional sense, but rather the curvature of space-time itself. It's the reason the Earth orbits the Sun, the reason light bends around massive objects, and the reason black holes warp reality into a nightmarish abyss of infinite density. Einstein's equations have passed every test we've thrown at them, from the precise precession of Mercury's orbit to the detection of gravitational waves rippling across the fabric of space-time. But as incredible as his theory is, it might not be the final word on gravity. The first cracks in Einstein's perfect universe began to appear in the early 20th century. Astronomers studying galaxies noticed something strange, something that defied every known law of physics. In the 1930s, Swiss astrophysicist Fritz Zwicky made a startling observation while studying clusters of galaxies. According to Newton's and Einstein's laws, the galaxies in these clusters should move at certain speeds based on the visible mass around them. But when Zwicky did the calculations, the numbers didn't add up. The galaxies were moving way too fast, as if some invisible force was pulling them. If general relativity was correct, then something was missing, something massive, something unseen. At first, the scientific community largely ignored Zwicky's findings, but decades later, in the 1970s, astronomer Vera Rubin confirmed his suspicions in a groundbreaking discovery. She observed individual galaxies, expecting to see their outermost stars orbiting slower than the inner ones, just like planets in our solar system. Instead, she found the opposite. The stars in the outskirts of galaxies were moving just as fast as those near the center. This was impossible, unless there was some mysterious invisible mass exerting gravitational influence. This invisible mass became known as dark matter, a hypothetical substance that doesn't emit, absorb, or interact with light in any way. According to modern physics, dark matter must make up nearly 85% of the universe's mass. But here's the problem. After nearly a century of searching, we still haven't found it. Physicists have built massive underground detectors, fired high-energy particles in colliders, and scanned the cosmos with the most advanced telescopes ever created. Yet, dark matter remains completely undetected. Some scientists are beginning to wonder, what if it doesn't exist at all? What if the reason we see these strange gravitational effects isn't because of some hidden mass, but because our understanding of gravity itself is flawed? This question has ignited one of the biggest debates in modern physics. If Einstein's equations don't fully explain gravity on the cosmic scale, then everything we think we know about the universe could be in question. The expansion of the universe, the nature of black holes, even our understanding of time itself. everything might need to be rewritten. And here's where things get even stranger. In recent years, new observations have thrown even more fuel on the fire. Some galaxies don't seem to follow the dark matter rules at all. Some appear to have far more of it than expected, while others seem to have none at all. On top of that, recent studies on gravitational lensing, the bending of light around massive objects, have produced results that don't quite align with general relativity's predictions. And then, of course, there are those deep space anomalies, the Pioneer spacecraft, the unexplained flyby maneuvers, the strange accelerations of probes leaving the solar system. Are these just coincidences? Or are they evidence of a deeper truth we have yet to uncover? Right now, the scientific community is at a crossroads. Some physicists believe dark matter is real and we just haven't found it yet. Others argue that we need a new theory of gravity, one that doesn't rely on invisible mass to explain the universe's strange behavior. And then, there are those who suggest something even more radical, that gravity itself may not be a fundamental force at all, but an emergent property of the universe, something deeper and stranger than we ever imagined. But before we dive into the revolutionary new ideas that could change our understanding of reality itself, let me ask you something. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Now let's take a closer look at the evidence. What observations are forcing scientists to question one of the most successful theories in history? What alternative explanations could actually replace Einstein's vision of gravity? And most importantly, if our understanding of gravity is wrong, what does that mean for the future of physics? The answers might just shake the universe to its core. The search for answers begins with a simple but unsettling question. If dark matter isn't real, then what's actually causing these mysterious gravitational effects? To answer this, physicists have started looking beyond Einstein's equations, searching for clues in the very fabric of space and time. And what they've found is nothing short of revolutionary. To understand just how deep this mystery goes, let's take a journey to one of the strangest places in the universe, the edges of a galaxy. Imagine yourself standing on a planet orbiting the farthest reaches of a spiral galaxy, 100,000 light-years from its brilliant core. From here, the stars appear sparse, scattered against the infinite blackness of intergalactic space. If Einstein's equations are correct, the gravitational pull from the galaxy's central mass should weaken with distance. Out here, your planet should be moving much slower than those closer to the center. But when astronomers measure the speeds of these outer stars and planets, they find something strange. They aren't slowing down at all. They're moving just as fast as the ones near the core, as if some invisible force is holding them in place. If gravity worked the way we expect, these outer stars should have been flung away into deep space eons ago. But they remain locked in orbit, obeying a rule that Einstein's theory can't fully explain. It's this baffling behavior that first led scientists to propose dark matter. But what if the answer isn't hidden matter at all? What if gravity itself works differently on these massive cosmic scales? This is where an entirely new way of thinking about gravity comes into play. Some physicists believe that Einstein's equations are incomplete, not wrong, but only a part of the full story. One alternative theory is called modified Newtonian dynamics, or MOND. Unlike dark matter, which assumes an invisible mass is warping space, MOND suggests that gravity behaves differently at extremely low accelerations, like at the outskirts of galaxies. According to MOND, when gravity becomes incredibly weak, it doesn't fade away the way Einstein predicted. Instead, it follows a different mathematical rule, giving galaxies just enough extra pull to keep their outer stars from flying off. Incredibly, MOND's equations perfectly match what we observe in real galaxies, without needing any invisible matter at all. At first, MOND was dismissed as a fringe idea. But over the years, as more data came in, some scientists began taking it more seriously. One of the most striking pieces of evidence came from something called the radial acceleration relation, a strange and unexpected link between the motion of galaxies and the amount of visible matter they contain. According to standard dark matter theory, galaxy rotation curves should vary based on how much invisible mass is present. But in reality, the pattern follows an exact formula, as if some underlying rule of gravity, rather than hidden matter, determines their motion. And here's where it gets even weirder. Mond's equations predicted this relation decades before it was discovered in real galaxies. But if Mond is correct, and dark matter isn't needed, then why does general relativity work so well everywhere? Else, why does it perfectly explain black holes, gravitational waves, and planetary orbits, but seem to break down when we look at galaxies? Some physicists believe the answer lies in something even deeper. A theory that doesn't just modify Einstein's equations, but replaces them entirely with something far more fundamental. One of the most radical ideas to emerge is the concept of emergent gravity. Imagine gravity not as a fundamental force, but as something that arises from deeper underlying principles, something woven into the fabric of the universe itself. This idea comes from cutting-edge research in quantum physics and string theory, where space and time are not smooth and continuous, but made up of tiny, discrete bits of information. According to this perspective, gravity might not be a force at all, but an emergent property of space-time, just like temperature emerges from the collective motion of atoms. The first hints of emergent gravity came from an unexpected place: black holes. Decades ago, physicists discovered that black holes aren't just massive objects. They actually store information in a way that resembles a hologram. The physics governing black holes looks eerily similar to the way information behaves in quantum mechanics. This led some scientists, like Dutch physicist Erik Verlinde, to propose that gravity itself might emerge from the interactions of microscopic quantum bits of space, what some call the holographic principle. If true, this would mean that what we experience as gravity is not a fundamental force like electromagnetism or the nuclear forces, but a side effect of deeper, hidden laws of physics. It would explain why general relativity works so well on small scales but seems to break down on cosmic scales. It would also mean that we've been looking at the problem of dark matter all wrong, not as a missing mass, but as a sign that our entire concept of gravity needs to change. But before we might rewrite the laws of physics, we have to ask, is there any real proof that Einstein's gravity is incomplete? Are there experiments, real measurable phenomena, that suggest something beyond general relativity? The answer, surprisingly, is yes, and some of them are downright shocking. Recent studies have found inconsistencies in gravitational lensing, the bending of light around massive objects. According to Einstein, the way light bends should follow exact predictions based on the amount of mass present. But when astronomers measure the gravitational lensing effects of galaxies and galaxy clusters, they find small but persistent deviations from what general relativity predicts. These discrepancies suggest that either dark matter behaves in a way we don't yet understand, or that gravity itself is acting differently than expected. And then there's the expanding universe itself. In 1998, scientists discovered that the expansion of the universe is accelerating, something no one expected. To explain this, physicists introduced dark energy, an unknown force that makes up nearly 70% of the universe. But some alternative theories suggest that what we're seeing isn't dark energy at all. It's a sign that our equations of gravity need to be modified on cosmic scales. Some models even suggest that space itself may have an intrinsic energy, an effect not accounted for in Einstein's theory. So where does this leave us? Right now, physicists are at a crossroads. Some believe dark matter and dark energy are real, and we just haven't found them yet. Others think Einstein's theory needs a fundamental overhaul, one that could lead to a new understanding of space, time, and the very nature of reality itself. But what if the answer is something even stranger? What if gravity is not just a force but a deeper phenomenon that connects everything in the universe, matter, energy, even consciousness itself? Before we dive into the truly mind-bending implications of rewriting gravity, let's take a moment to explore what would happen if Einstein's theory really were replaced. Would black holes still exist? Would time still function the way we experience it? And most importantly, Could this new theory unlock hidden aspects of reality that have remained just out of reach? The answers might be more incredible than we ever imagined. Imagine for a moment that everything we thought we knew about gravity was just a shadow of something deeper. What if Einstein's elegant equations, so precise that they predicted black holes and gravitational waves, were only an approximation of a more fundamental reality? If general relativity isn't the full picture, then everything from the way galaxies move to the nature of time itself could be different from what we've believed for over a century. To truly grasp the implications of rewriting gravity, we need to go beyond galaxies and cosmic expansion. Let's journey to the very edge of physics, to the strange, mind-bending realm of black holes. These cosmic monsters, the densest objects in the universe, have long been a testing ground for gravity. Their immense pull bends space and time to the breaking point, forming event horizons, boundaries where nothing, not even light, can escape. According to Einstein, if you were to fall into a black hole, your fate would be sealed, crushed into oblivion by an infinite gravitational singularity at the center. But here's the problem. Singularities don't make sense. They represent a breakdown in the very laws of physics, a place where general relativity simply stops working. This is where quantum mechanics enters the scene. Unlike general relativity, which describes gravity on large scales, quantum mechanics governs the subatomic world, the strange domain where particles can be in two places at once, teleport across distances, and even interact through spooky entanglement. These two theories, relativity and quantum mechanics, are both incredibly successful in their respective realms. But when we try to combine them to describe extreme gravity, like inside a black hole, they violently disagree. The equations break down. Numbers go to infinity. The universe, it seems, refuses to let them work together. Physicists have spent decades trying to reconcile these two pillars of modern science, searching for a quantum theory of gravity that would unite the macroscopic and microscopic worlds. And recently, a bold new idea has emerged, one that might not only explain black holes but also reshape our understanding of gravity itself. Some researchers now believe that gravity is not a fundamental force at all, but an emergent property of space-time. Think of a hologram. From a distance, it looks like a three-dimensional image, but up close you realize it's just a two-dimensional pattern, storing all the information needed to create the illusion of depth. What if the universe works the same way? This is the essence of the holographic principle, a radical idea suggesting that everything we experience as reality, including gravity, might be encoded on a lower dimensional surface. Black holes seem to follow this rule. Their event horizons store information in a way that behaves just like a hologram. But if this principle applies to black holes, could it apply to the entire universe? Could space-time itself emerge from a deeper level of physics, one that explains gravity as a byproduct of quantum information? Dutch physicist Erik Verlinde proposed an idea known as entropic gravity, which suggests that gravity is not a force in the traditional sense, but arises from the way information is distributed in space. In this view, gravity behaves like temperature, something that emerges from the interactions of countless microscopic components. Just as heat is the collective motion of atoms, gravity might be the collective effect of tiny quantum bits of space and time. And if that's true, then general relativity isn't a fundamental law, it's a statistical effect, an approximation of something deeper. This perspective changes everything. It suggests that black holes don't destroy information as we once thought, but instead encode it in a way we haven't yet fully understood. It also offers an alternative explanation for the effects we attribute to dark matter. If gravity is emergent, then perhaps what we're seeing in galaxies isn't the result of invisible matter, but of space-time itself behaving in an unexpected way on cosmic scales. But here's where things get even more bizarre. If gravity emerges from quantum information, then time itself might not be what we think it is. In our everyday experience, time seems to flow in one direction, from past to future. But in quantum mechanics, time is more fluid. Particles can interact in ways that seem to defy traditional causality. Some physicists now suspect that our perception of time is an illusion, a consequence of how information is processed in the universe. In this view, the arrow of time doesn't exist fundamentally. It emerges from deeper physical laws, just like gravity. And if that's true, then what happens inside a black hole? Traditional physics says that anything crossing the event horizon is lost forever. But if gravity and time are emergent, then perhaps the information inside a black hole isn't lost. It's just stored in a way we don't yet understand. Some theories suggest that the interior of a black hole might be connected to another region of spacetime, possibly even another universe. Could black holes be cosmic gateways, revealing the deeper structure of reality? Recent research has provided intriguing hints that these ideas aren't just speculation. Scientists analyzing gravitational waves, ripples in spacetime caused by merging black holes, have noticed subtle discrepancies that could point to new physics. Some alternative gravity theories predict additional signals in gravitational waves, effects that wouldn't exist if general relativity were absolute. These anomalies, while small, suggest that our understanding of gravity is incomplete. And then there's one of the strangest concepts of all, the possibility that our entire universe might be a kind of cosmic hologram, a three-dimensional projection of a more fundamental lower-dimensional reality. This isn't just philosophical speculation. Real calculations based on string theory suggest that certain aspects of gravity can be described this way. If true, it would mean that space, time, and gravity itself are illusions, emerging from a deeper layer of physics beyond our comprehension. So if Einstein's theory is incomplete, what comes next? If gravity is not fundamental but emergent, then what underlying laws create it? Could we harness this knowledge to manipulate gravity, control time, or even access other dimensions? And if gravity is an illusion, then what does that mean for our very perception of reality? Before we attempt to answer these mind-bending questions, we need to take a step back and ask, what would it mean for humanity if Einstein's theory is truly replaced? Would it change our ability to travel through space? Would it reveal new ways to bend and manipulate the fabric of reality? And most importantly, if gravity is just an emergent effect, then what deeper force is actually governing the universe? The implications are staggering, and in the final section, we'll explore just how far this rabbit hole goes. If Einstein's theory of gravity is incomplete, then we are standing at the threshold of a new era in physics, one that could unravel the deepest secrets of the universe. The idea that gravity is not fundamental but emergent challenges everything we thought we knew. But what does this mean for our understanding of reality? What happens when we rewrite the rules that have governed physics for over a century? Let's take a moment to grasp the sheer scale of what's at stake. If gravity is an emergent property of space and time, then everything we take for granted, motion, force, even the passage of time itself, might not be fundamental features of the cosmos, but illusions created by a deeper hidden structure. This isn't just a mathematical curiosity. It has real, tangible consequences. If we can uncover the true nature of gravity, we might unlock the ability to manipulate it. Think about that for a second. Artificial gravity, gravity shielding, or even gravity-based propulsion, ideas that once belonged to the realm of science fiction, could become reality. Imagine a future where spacecraft no longer rely on massive fuel tanks but instead generate their own gravitational fields, bending space-time around them to travel vast distances in an instant. If gravity is emergent, could we control the fabric of space-time itself? Could we shape gravitational forces the way we currently manipulate electricity and magnetism? Some scientists believe that if we decode the quantum structure of space-time, we might one day engineer gravitational fields in ways we never thought possible. And if that's true, the dream of interstellar travel might no longer be a dream at all. But there's an even deeper implication, one that shakes the very foundations of physics. If gravity is not fundamental, then what is? What lies beneath it? Some theories suggest that space-time itself is woven from a quantum network, a vast web of entangled information. In this view, space and time don't exist independently. They emerge from a deeper set of relationships between quantum bits of information. And if that's true, then the universe is not a collection of objects in space but a computational structure, something that behaves more like a vast cosmic simulation than a classical physical system. This brings us to one of the strangest and most controversial ideas in modern physics, the notion that we might be living in a holographic universe. The holographic principle, which suggests that our three-dimensional reality is a projection of information encoded on a lower dimensional surface, isn't just theoretical speculation. It has mathematical backing from string theory and has even been observed in black hole physics. If this principle applies to the entire universe, then what we perceive as physical reality may be nothing more than a sophisticated illusion, one governed by an underlying layer of quantum information. But if reality is holographic, then what does that say about our place in the cosmos? Are we just patterns of information playing out in a grand computational process? Some physicists believe that understanding this could lead to breakthroughs in quantum gravity, perhaps even a unified theory of everything. Others suggest that if space-time and gravity emerge from quantum information, then consciousness itself might be part of this same fundamental process. Could the way we experience reality be directly linked to the deep, hidden structure of the universe? Now, let's return to Einstein for a moment. His equations have shaped modern physics, guiding our understanding of the cosmos for over 100 years. They have been tested in extreme conditions, from black holes to gravitational waves, and have held up every time. But if we've learned anything from the history of science, it's that no theory is absolute. Newton's laws were once thought to be the final answer, until Einstein came along and revealed a deeper truth. Now we may be on the verge of another revolution. If gravity is emergent, then Einstein's equations, as brilliant as they are, might just be an approximation of something deeper, a shadow of an even greater reality waiting to be uncovered. The search for this deeper truth is happening right now. Physicists are using gravitational wave observatories to test for tiny deviations from Einstein's predictions, looking for signs of new physics. Quantum experiments are probing the structure of space-time itself, searching for evidence that space and time are not continuous, but made of discrete units, like pixels on a screen. And theorists are pushing the boundaries of string theory, quantum gravity, and the holographic principle, trying to uncover the fundamental nature of reality. So, what comes next? Will we soon witness the dawn of a new era in physics, one where gravity is no longer a mystery but a tool we can control? Could we one day harness the true nature of space-time to unlock new dimensions of travel, energy, or even consciousness itself? Or is there yet another layer of reality beyond even this, waiting to be discovered? One thing is certain: physics is not finished. Einstein's theories may have been a masterpiece of human thought, but the universe is not done surprising us. As we continue to explore, experiment, and push the limits of our understanding, we may soon find ourselves staring at an even grander, more mysterious truth, one that changes not only how we see the universe, but our very place within it. What do you think? Could Einstein's theory of gravity be just one step on a much longer journey? Could our entire understanding of reality itself be on the verge of transformation? Let's keep this discussion going in the comments. I'd love to hear your thoughts. And if you enjoyed this deep dive into the mysteries of the cosmos, don't forget to like and share this video with fellow science enthusiasts. Until next time, keep questioning, keep exploring, and never stop wondering about the universe.